All right, hi everybody. Welcome again to 10600. So today we're going to look at how to work with matrix differentials. So let's get started. I think the first thing that we should do is go back over some of the content that we looked at yesterday. Which is to say Monday. All right, so we looked at scalar derivatives and vector derivatives and how to take derivatives of common functions. And it seemed like everybody was had scalar derivatives pretty well down, but people needed some more intuition about what vector derivatives are. And so let's start with that then. So suppose that we have a function like this, f, that takes a single real argument and goes into Rn, right? So it's a function that takes a scalar and outputs a vector. We can think of a function like that as corresponding to a curve in Rn. So as we vary the argument x, we trace out this curve here. And the derivative at any point is a tangent vector to the curve, right? So at this point marked with a circle, the derivative of the function is going to be this red vector pointing out that way. And each component of the vector tells you the slope of that tangent vector in one of the coordinates, right? So the x component tells you the slope of the tangent vector in the x direction, y component in the y direction, and z in the z direction. Let's see. And what I mean by that is that, for example, if you divide through by the z coordinate, right, you'll get the you will have normalized it so that motion in the z coordinate is at unit speed, and then the x coordinate will be the slope in the x direction, and the y coordinate will be the slope in the y direction. All right. So as another example, we could have a function with a vector argument and a scalar output. Right, the previous one was a scalar argument and a vector output. Here the other way around. And we can think of this as being a surface, right? So here is a function in R2 to R, right? It's just a quadratic function like this. And the derivative at any point tells you the direction of steepest increase of that function, right? So here at this point marked in red, I've put a contour plot of the function below a usual surface plot, and at this point in red, the gradient is pointing that way, and it tells you the direction of steepest increase. And just in general, if you're working on a if you're working with a contour plot, right? So if you have a contour plot that looks like this, right, where you have some contours of the function, right, and they work like they go up like this, right? So there's my sketch of a contour plot. At any given point, the gradient vector is going to be the direction of steepest increase, and that means that it's going to be orthogonal to a contour, because a contour is the direction in which it stays the same, and then uphill is going to be perpendicular to across the hill, right? And so again, you could have a gradient like that, and another one like that. All right, so that's interpreting derivatives of functions that involve vectors. So I want to add, by the way, that you can also do functions that involve, let's say, a vector input and a vector output, or even a matrix input and a third order tensor output, right? And that gets obviously harder to visualize because you're working in 5 dimensions or something like that. But in general, the rule is always that you can take the derivative of any one of the outputs with respect to any one of the inputs, and that's a partial derivative. And the derivative of the whole thing is just going to be a matrix or a tensor that has as components all of those partial derivatives, right? And so what you can do is you interpret each one of those elements as telling you the slope of one of the dependences. Let's say the dependence of the fourth output on the second input or something like that, right? So okay. Let's see. Could I explain the example on squared error? Yes, I definitely will explain that example on squared error, and I'm going to. I'd like to finish going through the pictures that I added first, and then that was going to be the next thing I do after that. So let's take a look at. I just have a couple more pictures to show, and those are the pictures of the Taylor series. Right. So a Taylor series is taking a nonlinear function and approximating it locally at a point with a linear one. And so here's an example of our nonlinear function, right? This is a vector-valued function. The output is in R3. And at this point right here, I can take its Taylor approximation, and that's going to be a tangent line, right? It's going to touch at the point that I take the approximation around, but it's going to proceed linearly out instead of following the curve, right? And then the same thing can happen with a surface, right? So again, I'll take the Taylor approximation at this point right here, and I'll get a surface that is tangent. This is a linear surface that is tangent to the original nonlinear surface, and that's the Taylor approximation, right? And so always just in general, we're taking some nonlinear function and approximating it with a linear function. And if it's in a low enough set of dimensions for you to plot, it's always going to be a tangent. I mean, it's always going to be a tangent, but you can see that it's a tangent when you can make a plot. And that means just that the plane is going to smoothly touch the function at one point. All right. So that was all I wanted to review from Monday's notes, right? And here's the example at the end, the squared error example, and we're gonna do that example. We're gonna do that example over using the actual rules for working with differentials, right? So there's two ways to do it, right? You can always calculate a differential this way, right? Which is to say you write out each yi as a function of all of the xj's that involves usually tons of summations and lots of keeping track of indices. And then you can take the derivative of each component, the partial derivative of each component of the output with respect to each component of the input, and then you can reassemble them into an expression that shows you the differential, right? And that's it's always good to know that you can do that, because if you ever get confused about how to work with an expression that involves differentials, you can always fall back on doing it component-wise, right? And so as you get practice with working directly with differentials, it can be much faster and easier to do it directly on the differentials, but you can always, if you're not sure, check your work by going back and doing the derivative component-wise. All right, so what are these rules that we're going to use to work with differentials? Let's grab another set of notes and put them up here on the screen. All right, so in order to work with differentials, another good thing that you can do to make sure that you've gotten everything right, to check your work, is to do type checking, right? So if you have a function, right, some function f that depends on some variable x, and x is in the vector space u, and f of x is in the vector space v. The differential is then going to be some function that involves both x and dx, right? And so that represents a function, df, which takes an argument x and another argument dx. Both x and dx are in the vector space u, and the output is still in the vector space v, because we're trying to approximate the output of f, which is in v, right? And this function is always linear in the dx argument, but it's typically nonlinear in the x argument, right? So if we go back to our example, right, we had that d of ax minus b norm squared was equal to ax minus b transpose a dx, right? So this is this here represents a function of two variables, x and dx, right? And it's linear in x. It also it's linear in dx. It also happens to be linear in x, but it doesn't have to be, and we'll see examples later where it's not, but it will always be linear in dx. Right, and so this here, df of x and dx, this is the long form of the notation, right? And the short form looks like this, right? So we would say that df is equal to the differential of that expression is equal to this expression that has the differential of x in it, right? So this is the short form of the notation. We don't explicitly write the arguments of f, but if we did write the arguments, they would be x and dx. Now, just to keep things confusing, if we have f of x equals ax minus b norm squared, it also makes sense to write df of x, right? And what that means is parenthesizing like this. We're taking the differential of the expression f of x, right? And if we parenthesized it this way, right, where df was a thing, then we would have to have two arguments, x and dx, right? And so often, as always, we omit parentheses when they're clear from context. And in this case, they are, because in this case, there's no dx argument, and in this case, there is one. So we can write both df of x and df of x dx. And the first one gets parenthesized like that, and the second one gets parenthesized like that. And so what I mean by type checking is that, oh, you're right, derivative should have been multiplied by 2, and so we can fix it like that, putting in the half. I believe it was right in the notes. The professor just forgot to write down the half when he copied it. All right. So what I mean by type checking is just that, for example, when you go through your expression, if there are two matrices that get multiplied, make sure that they match dimensions, right? That there's an if there's an m by n matrix and an n by k matrix, you can multiply m by n by k, but you can't multiply in the opposite order, for example. Or if you are applying a function to an argument, you can make sure that that function expects an argument of the same type as the argument you're giving it. And just as compiling your code catches a lot of syntax errors, type checking your math will catch a lot of silly, simple mistakes that you can make in writing it down. All right. You can do a differential of an expression with multiple variables, and that represents a function with two sets of arguments, the original variables and the differentials of the original variables. And it's linear in the differentials, but it's nonlinear typically in the original variables. And another way of saying that is that df is multilinear in dx, dy, and so forth, right? So we already talked about bilinear. That means linear in each of two arguments when you hold the other one fixed, right? So, you know, x times y is not a linear function, right? It's a quadratic function if you think of it as both x and y, but it's linear in x with y fixed, and it's linear in y with x fixed, and so we call it bilinear. And x, y, z is trilinear, or we usually just say multilinear once we get above two variables. All right. Now, while we're on the subject of notation, there is another common notation, which is that f prime of x would be equal to ax minus b transpose a, right? So f prime is another notation for the Jacobian in this case. It's the derivative of a vector function with a vector output. And this sort of notation is probably more familiar, but you can map them back and forth by the simple rule that df is equal to f prime of x dx, right? So f prime is just the coefficient of dx in this linear function up here. All right, so now we finally get to the rules for working with differentials. And these are rules that you should make sure that you know very well, because they're what let you actually do calculations that involve differentials, that let you take derivatives quickly. So the first one is linearity. If you have, so the differential is a linear operator, meaning that if you have the differential of ax plus by, that's a dx plus b dy, where a is a constant and b is a constant and x and y are variables, right? And you can also do it for sums. The differential of a sum of functions is the sum of the differentials of the functions. If you have a term that doesn't contain any variables, in other words, a constant, when you take its differential, it's 0, right? So in particular, if we had the differential of ax plus dy plus c, that would be a dx plus b dy again, and the c would vanish. All right. So that one is fairly simple to use. And then, as always, we will have a chain rule and a product rule, right? And those are going to be your three big tools: linearity, chain rule, and product rule. There are also a bunch of identities, like the derivatives of specific functions, that are good to know, but the three sort of general rules are linearity, chain rule, and product rule. So if you have the differential of f of g of x, where f and g are two functions that match types appropriately, right? The output type of g is the input type of f. Then the differential of the composed functions is f prime of g of x times dg of x, right? And here the dot stands for matrix multiplication, otherwise known as composition of linear operators. And so this is using several shorthands that we've defined above. The long version is this one down here, which you can see is a little bit harder to read, but it's more precise, I guess, if you're not used to the shorthands. So in general, whenever you read a function like this, we're going to consider the variable x to be fixed, right? And the differentials are the things that are changing. So here, for each fixed value of x, f prime of g of x is itself a function from v to w, right? It'll take a change in its input and produce a change in its output. dg of x, again for each fixed x, will be a function from u to v that takes a change in its input, the u, and produces a change in its output, the v. And so we can then compose those two things. We can take any du, apply dg of x to that, get a dv, apply f prime of g of x to that, which takes a dv to a dw, right? And if you write that out using the two-argument version of the differential, right, what that means is we take the differential of g evaluated at x and dx, pass that result as the change argument to the differential of f, which we evaluate at g of x. And by the way, this chain rule is a complete generalization of the chain rule that you probably learned for scalars. And so, it's worth going through a couple of scalar examples to make sure that you can see the correspondence in notation. All right, product rule. Same thing, if we have f equals g times h, where times here is matrix multiplication again, otherwise known as composition of linear operators. If we take the derivative of g times h, right, the differential of f is the differential of g times h plus g times the differential of h, right? And I've written out all of the types here, and also the long form here, and it's worth staring at this for a little bit to convince yourself that in fact we are doing the correct thing, that this expression type matches. And you can see it gets a heck of a lot messier when we don't use the shorthand. And as usual, the product rule keeps going for 3 or more terms in the product. All you do is you iterate over the terms, f, g, and h, and you take the differential of each one in turn while leaving the other two the same. So here f is the same, h is the same, we're taking the differential of g, and f and g are the same, we're taking the differential of h. And then you just add up all of those results. All right. Oh, and by the way, the product rule, I stated it for matrix multiplication, but in fact, it works for any multiplication-like operator. What do I mean by a multiplication-like operator? I mean something that's bilinear or multilinear in its arguments. So matrix multiplication is an obvious example of that. It's linear in each one of the matrices when you hold the other one fixed. But ordinary scalar multiplication works, so do dot product and cross product. Also component-wise product of matrices or vectors. And if you remember from earlier in the semester, we used component-wise product with broadcasting to handle probability tables, and that's a multiplication-like operator as well. And because there's a lot of different things you can do with matrices and tensors, people have defined a ton of different multiplication-like operators that we haven't yet worked with and may not get a chance to work with in this course. Those include tensor product, Kronecker product, Cauchy-Rao product, and probably a zillion others that I haven't thought of. And so if we take an example with the Hadamard product, here represented by the little circle, the differential of f times g is the differential of f times the differential of g plus f times the differential of g, right? And so the product rule just holds for every single one of these. The only thing you have to worry about is commutativity, right? So scalar multiplication is commutative. You can reorder the arguments. Matrix multiplication is not, and so you have to keep the arguments in the same order. And if you type check, you'll catch any mistakes you make that way, because the input to df should be the output type of g. But it's very easy to accidentally reorder the products if you're used to dealing with scalars. All right. So people are asking, go over the type checking in section 7 in detail. Yeah, sure. That makes a lot of sense. So, all right. So let's write out the types of everything, right? So we have f equals g times h. So f is a function which goes from whatever vector space x is in to a matrix or a linear operator from u to w. That means that df is from the same vector space, but two copies of it, one for x and one for dx. And that goes to that same vector space of matrices or linear operators from u to w. And similarly, g of x, it takes an x and it goes from v to w, and h goes u to v, so that we can compose an h with a g, u to v and v to w. And then dg and dh are the same. They take an x argument and a dx argument, and they produce two operators that you can compose, right? And so when we type check this, right, what we do is for each fixed x, so for a fixed x, g of x is in v to w, dh of, and for a fixed x and dx, dh of x dx is here, it's in u to v, right? And so u to v composed with v to w, the v output of dh matches the v input of g. And so this part of the expression type checks, right? And it will give us an operator from u to w, passing through v, right? So this here, for any fixed x and dx, this gives us an operator from u to w, right? So let's actually write that out. Right, so we have g of x for fixed x, that's of type v to w, and dh of x dx, fix x and dx, that gives us u to v. Therefore, if we compose them, g of x composed with dh of x dx, that goes from u to v, then v to w, and so it will be of type u to w. Okay? And then we can do the same thing for this half of the expression, right? So dg of x and dx, that's if we fix x and dx, that goes from v to w. H of x, if we fix x, that goes from u to v. And so dg composed with h, that goes from u to v, v to w, so it goes from u to w. And now we have two terms, one that goes from u to w here, another one that goes from u to w there. If we add them, we get another term that goes from u to w. And they type check, meaning that they're elements of the same vector space, the space of functions from u to w, and so it makes sense to add them. And then this whole thing, for each fixed x and dx, represents a function from u to w. And so the type of df of x dx should be a function from u to w for each fixed x and dx. And in fact, we got a function from u to w, and so the whole thing type checks. All right? And you can see that the type checking is by no means obvious, right? You have to actually go over it in detail to make sure that everything is right. If you followed the product rule correctly, which of course your professor has never made mistakes in following the product rule, haha. But if you follow the product rule correctly, you will get an expression that type checks automatically. Why are the operators G and H not of the same input space, since they both have X as their argument? G and H do have the same input space, right? So here, G is a function that takes an input X, H is a function that takes an input X. G of X and H of X are not the same input space, right? If you provide an X, then you get a value of type V to W. If you provide an X, you get a value of type U to V, right? And so G of X and H of X do not have the same input type, but G and H do. They both take an X. Right? And so it's when you're type checking, it always is helpful to think of some arguments as being provided and other arguments as being left not provided, so that some of your values are still of function types, right? So here, the x and the dx, right, appear explicitly, and so we're going to consider those to be fixed. And then when we write this expression, once we've provided the x and the dx, we get some value that is itself of a function type, and that makes sense as an argument to the function composition, right? And so it's always essential to keep track of which, when I wrote here, right, for fixed x and dx, which arguments are being provided, filled into the function, and which arguments you're thinking of as still yet to be provided, right? And we typically leave the yet to be provided arguments implicit, right? So g of x is a function from v to w. We don't have an explicit name for the argument of type v or for the output of type w. All right, so let's go back now to our example of squared error, right? So we already wrote out that y is equal to ax minus b transpose times ax minus b over 2. If we take the differential of that, it's actually quite fast to do that using the rules that we used before, right? So dy, we just use the product rule, right? There's one term ax minus b transpose and another term ax minus b. And so we get d of ax minus b transpose times ax minus b, and then ax minus b transpose d ax minus b, both divided by 2, right? And so that's just an application of product rule. Now, these are both scalars, right? It's vector transpose times vector. And so a scalar is equal to its own transpose, right? And that means that these two terms are actually the same. And so we can combine them and get rid of the half, right? And then d of ax minus b, we just use linearity. d of ax is a times dx. d of b is 0 because b is a constant. And so we get just a dx for that term. And so you can see this is, in a lot of ways, much, much faster than it was to do it the component by component way. And also, there were no fiddly little I, j, k, and l that we would lose track of, right? One of the things that's really easy to do is when you are dealing with an expression that has 4 different indices in it, it's really easy to get the indices mixed up. And so this notation hides all of the indices and manipulates them automatically for you. And so it's really powerful in avoiding index errors. And this is not by any means an expression that there's a large advantage for with this notation. There are, hopefully we'll see later, some examples where you can't even write down the derivative in any compact way using standard notation, so that if you tried to write it down, it would be several lines of detailed code using indices, whereas if you actually just use the differential notation, it'll be half a line that's relatively easy to understand. All right, so I think at this point it might make sense to start doing some examples. So let's, I wrote down a few examples to do. So let's start with this example. We're going to define a function called s. S of z is equal to 1 over 1 plus e to the minus z. Okay? Some of you may have seen that function before. It's called the logistic sigmoid. It looks like this, if I can draw it, where it goes up to 1, it starts at 0, it hits a half when you cross the origin, yeah, it's called a sigmoid because it's kind of S-shaped. And we're also going to define the function s, which maps Rn to Rn by s of z, the ith component, is equal to s of zi, right? So this just means we apply the function s component-wise to every component of a vector. So now, we can take the differential of s, right? Just the scalar version. So ds is equal to d of 1 plus e to the minus z inverse, right? And you know the rule for polynomials, right? So that is 1 plus e to the minus z to the minus 2 times minus 1. And then we take the derivative of what's inside, so d of 1 plus e to the minus z. And that's equal to minus 1 plus e to the minus z to the minus 2 times d of this, right? D of 1 is 0 because 1 is a constant. D of e to the minus z, the derivative of e to the something is e to the something. So this will be e to the minus z, d of minus z, right? These two minus signs cancel, and we get e to the minus z over 1 plus e to the minus z squared dz, right? So this is just a scalar example, but you can see that the chain and product rules work pretty much as expected. This function here, we can take its derivative, right? And so the type of this function should be, it takes an Rn, and it gives an Rn, right? S does. And so for each fixed z, ds will take a dz in Rn and give us a ds in Rn, right? And so for this one, ds is going to be, well, let's see. So the off-diagonal, so it's going to be a matrix, right? Because it's going to be a function from Rn to Rn. And the off-diagonal elements are going to be 0 because component I of the output doesn't depend on component j of the input if j is not equal to I, right? So it's going to have zeros on the off-diagonal. And then it will be, right, so this here, right, this we'll call S prime of z, right? And so we'll get just S prime of z1 down to S prime of zn times dz, right? And so here dz is a vector, and we're component-wise multiplying by S prime of z of zi for each I, right? Another way to write this, since we just looked at Hadamard product, this is going to be S prime of z Hadamard product with dz, right? So that means every component of z gets multiplied by the corresponding component of S prime of z, where again we're defining S prime to be a function that acts component-wise. All right, so now let's get a little bit more complicated. Let's take the differential of a times, the differential of S of a times z, a times x plus b, right? So here z is equal to ax plus b. So that's going to be first we use the chain rule, right? So we're going to get S prime of ax plus b Hadamard product d of ax plus b, right? And here you can either write Hadamard product the way I did here, right? So this is just using the chain rule with this expression we used here, substituting ax plus b for z. And you can write it this way as well, right? You can write it with a diagonal matrix if you prefer. But now we get to use, well, let's continue here, right? So this is equal to S prime of ax plus b Hadamard with a dx, right? Because d is linear, it goes through the a, and d of a constant is 0. Right? And so here, if you've done neural nets or deep nets, you might recognize this as an expression for one layer of a neural net. And we've gone through and we've done the derivative with basically 2 lines of work. And actually, typically you just skip this line and directly pass the d through the ax plus b, but I wrote it out in detail. Right? And so all that you need to know is this expression for the derivative of the nonlinearity, right? And then you just use this in the chain rule to get this, right? And later on, we can take, later on we'll show how to take the second derivative, and I'll come back and give you the second derivative of this expression. All right, so let's do an example now where you guys can try working on it, and then I will give the right answer after you guys have a few minutes to work on it. Right? So let's suppose that we have a probability distribution, p of x, over a discrete random variable x, which will be 1 up to, let's say, n, right? So we know that sum from I equals 1 2n of p of x is equal to 1, right? So now let's give a functional form for p of x. We're going to say that p of x is equal to e to the x Actually, I'm going to make this just slightly more interesting. Actually, let's leave that. It'll be e to the t of x dot theta, right? So t is going to be a function that goes from 1 to n to rk, and theta is going to be a vector in rk, and so we can take their dot product. And then divide by a normalizing constant z, which is going to depend on theta, right? So I've written here, if you happen to recognize this as an exponential family of probability distributions, that's fine, but you don't need that for this exercise. I've just written some form for the probability distribution of x. And as usual, z of theta is defined by the fact that it has to sum to 1. All right. And for convenience later, so that everything stays inside the exponential, I will write g of theta equals the natural log of z of theta, which means that p of x, we can write this as e to the t of x dot theta minus g of theta. All right. Okay, so I've done all of that derivation just to get to this line here. You can actually forget about all of the derivation above this if you want to. It's just there so that you can interpret the notation here. But what I'm going to ask you to do is to take the differential of both sides of this equation, right? So if this function is equal to this function, then the differential of this function is equal to this function. So what I would like you to do is to write down the equation d of sum I equals 1 to n of e to the t of x dot theta minus g of theta is equal to d of 1. And I'd like you to write this out and simplify it as much as possible. All right? And I'll give a few minutes for people to ask questions and or work on this. And then I'll show the answer. This is not a graded exercise, but it should be good practice. So I'm getting questions about what people should take the derivative with respect to. That is an excellent question. So the variable x is bound by the sum, right? And so you can't take the derivative with respect to that. There's only one free variable in the expression, which is theta, right? So take derivative with respect to theta, right? And it appears twice in the expression. So make sure that you take derivative with respect to theta and pay attention to both of those appearances. So one more hint when you're doing it. You don't have to expand out the derivative of g of theta. So you could expand g in terms of z if you wanted to, and even in terms of this sum, but it's okay to leave the expression in terms of g and its derivative. All right, so let's go and take a look at the solution. Somebody pointed out, by the way, that I made a typo. This should be the sum over values of x, not the values of I. There is no I. I apologize for that. All right, so let's do the differential. So the differential just goes, so on the right-hand side, the 1 is a constant, so the differential of 1 is 0. That was the easy part. Let's do the left-hand side. The differential just goes through the sum, so we have the sum from x equals 1 to n of d e to the t of x dot theta minus g of theta, right? That's equal to sum x equals 1 to n. All right, so the derivative of e to the z is just e to the z, so we'll get f prime of g of x, which is what is happening here? All right, I don't know what's going on with the whiteboard. For some, it's gotten all right. It fixed itself at random. Lovely. T of x dot theta minus g of theta, right? So this is f prime of g of x times d, sorry, in the chain rule. So in the chain rule, right, I shouldn't have said f prime of g of x because I'm already using g for something else, but d of e to the something is the derivative of e of the something times the derivative of the something, which is to say t of x dot theta minus g of theta, right? And that's equal to sum from x equals 1 to n e to the, well, actually, before I write that out, I'm just going to recognize that this is another expression for p of x, right? This is just a copy of the original expression for p of x right here. So I'll just write that, p of x, and then d of this, right? So that's going to be t of x d theta minus g prime of theta d theta, right? And that is equal to 0. And so that's the solution to the exercise, right? And if you wanted to, you could actually simplify it even more using what we know about probabilities. So sum from x equals 1 to n, p of x, t of x, right? That's just the expected value of t of x. So this is saying the expected value of t of x, right? Here, sum from I equal to 1 to n, p of x, g prime of theta. Well, g prime of theta doesn't have an x in it, right? So we'll write that out, right? We can just factor the g prime out. So it'll be g prime of theta times d theta times sum x equals 1 to n p of x. But sum from x equals 1 to n p of x, that's just 1. So we can cross that out. And so we have that the expected value of t of x is equal to, oh, I forgot to write a d theta on this side of the expression. E of t of x d theta is equal to g prime of theta d theta, right? So now we've simplified it even further. So I would expect that people who haven't seen this before would get to this part. But if you were paying lots of attention to the probability part of the course earlier, you would see you would be able to simplify even further to this part, which says that the expected value of t of x is just g prime of theta, which is kind of an interesting identity. And that identity turns out to be useful for a lot of things much later on in your study of probability and machine learning. All right, so please feel free to ask questions about the example. Otherwise, I'm going to move on to more about differentials. So, we've done first derivatives so far. The next obvious question is how to do second derivatives. So the first differential was a function of x and dx, and it was linear in the dx argument, but not necessarily in the x argument. We can take the differential again, and we'll want to take it with respect to the x argument. And that's called the second differential, and it's written d squared f, and it still has the same two arguments, x and dx, right? And so if we write g sub dx of x, that's going to be f of x dx. So I'm just highlighting that this is an argument, that x is the argument, and we're fixing dx. So d squared of f is just the ordinary differential of g sub dx, right? So you take the differential once to get g, and you take it again to get the second differential. And the interesting thing, or something to pay attention to, is that the same value of dx gets put as an argument to the second differential and again to the first differential, right? And that means that if the first differential was a linear function of x, the second differential is a quadratic function of x. Sorry, of dx, and the second differential is a quadratic function of dx. And so we can continue the interpretation as a Taylor expansion. So where the first differential was a linear Taylor expansion of the function at a point, this is a second order Taylor expansion, meaning it's a quadratic approximation to a function in the neighborhood of a point. So how do we compute the second differential? It's actually very much like computing the first differential. You can compute the first differential and then take the differential again to get the second differential. The only rule that you need beyond the ones we've already discussed is that pre-existing copies of dx are treated as constant. So for example, this is just copying, oh, I forgot the over 2 again. I'll fill that in. If we take the first differential of this, it's that. We computed that earlier. And if we take the second differential, we just take the differential of that again, so d of that. And by linearity, we just push the differential inward to get, the b vanishes, we get a times dx, and the a and dx stay the same because this dx is treated as a constant. And so we get dx transpose a dx, right? And so the second differential is really just like the first differential, except that, as I said before, we get a quadratic function of dx instead of a linear function. And if we have multiple variables, all of the previous differentials, we consider them to be constant, and we take the differential again with respect to the original variables. And so here's an example. F of xy is cos x sine y. Then df is, okay, product rule. Derivative of cosine is minus sine, so we have minus sine x sine y dx, right? So d cos x is minus sine x dx, and then sine y, we're treating it as constant this time, and so it just comes through. And then the second one, the derivative of sine is cosine, and so we have cos x, that stays because we're in the second half of the product rule, and then cos y dy for the differential of this term, right? And then we do it again, and we apply the product rule to this term, and we get, when we do the first term, we get the sine x turns into cos x dx, so we get cos x dx times sine y dx, so cos x sine y dx squared, right, with the minus sign that carries down. And then the second half, right, we keep minus sine x and dx constant, and then d of sine y is cos y dy, so we get cos y dy, right? And we can do the same thing to this term to get these two terms. And we get the same, we get a process very similar to taking the first differential, but now we get a quadratic function, so we'll have products of differentials. We could equivalently do it in vector notation. So I've written out the same thing in vector notation. Make this a little wider so we can see the whole thing at once. Right, and there's no additional insight in this case from writing it out in vector notation because the definition of x treats x1 and x2 completely separately. But it's a good example. You get a quadratic function of two vector arguments, which is to say vector transpose matrix vector. And we can keep on going and going. We can get third and higher differentials. The third differential is a cubic function of dx. The fourth is a quartic function, and so on and so on. The utility of taking higher differentials gets less and less, I guess. But first and second are both pretty common. And again, when you start taking higher order differentials, you can wind up getting quite complicated looking functions. But these functions would wind up being a real bear to express in terms of the original component-wise notation. And so the more derivatives you take, the more you save. Act now, right? Supplies are limited. All right, so I think rather than starting a new topic, we will go ahead and close off here. My office hours start now and they'll go until 3:30. So see you guys on Monday, and thanks a lot.